Hello and welcome to Silux, the podcast where we talk about scientific developments and technological changes, normally in Luxembourg. But again, this is the month of the international episode. European scientist is visiting, so we'll be talking European science, but not so far away from Luxembourg. And this means that our guest today is Andreas Zeller. Andreas Zeller is faculty at the CISPA Helmholtz Center for Information Security and professor for software engineering at Saarland University. Andreas is one of the few researchers to have received 2 ERC advanced grants, and we'll be talking a lot about software engineering and fuzzing and testing and everything, and I'm very excited to do that today. Andreas, thank you so much for coming.
Happy to be here with you today.
So we already had a guest who actually was the reason why I wrote to you. So we had Jordi Cabot, who is now based in Luxembourg, and we were talking about software engineering with him. And he said, you need to talk to Andreas Zeller. So now, listeners, if you're interested, of course, please do listen to the episode about software engineering with Jordi Cabot. This is kind of the base, but it's always interesting to know from a different researcher where the field is, because everybody defines it a bit differently and sees it differently, I think, as well. So where is the research in software engineering right now for you?
It's a nice thing that you ask, because that's also a common debate among software engineers, of course, where the field is going. Basically, I see the field being not necessarily split, but focusing on 2 areas. One is the area that is concerned with building software that works, and not necessarily me all alone sitting in some corner and building something. That's what we would normally call programming. Of course, programming is much more than that. But in software engineering, I'm mostly concerned with big software that is being developed in big teams, and this development needs to be organized in some form. And in particular, when you start building software, because at the beginning you just have an idea, you have maybe a set of requirements, building this in a systematic fashion is very difficult, because you have so many difficult or different tasks to coordinate and to organize. And you have to make sure that people don't step on each other's feet, and that the software that you develop actually also satisfies all the requirements. So this first half of software is concerned with building the software. That is, out of nothing, create a piece of software. And the second half of software engineering is concerned with software that is already around. And there we are talking about maintaining this software, which also includes adjusting it to new requirements, which means evolving it further, which also means analyzing it, testing it, checking that it satisfies the requirements, and also after a change, that it still satisfies the requirements. It's a bit like architecture, and on one side you're talking about, well, here's my green field, and I can imagine something entirely new, and I'm building it from scratch. Or maybe I'm tearing something down beforehand, but then from there on I build something entirely new. Here I am. And the other part of software architecture is concerned with maintaining all the buildings that we already have and updating them to the newest building standards, occasionally replacing a window, putting in an elevator and whatnot. But the interesting thing is that these 2 fields, or these 2 aspects of software engineering, have very different demands. On one side, it's more about, imagination and coordination. And on the other side, it's more about dealing with what we already have, and sometimes also figuring out what we already have. Because like with real buildings in the real world, you do not necessarily always have nice detailed plans on how the software works and how it should be maintained and all the things that you need to take care of. Sometimes you just find a building, there you have, maybe without any plans or anything. Well, and then your first job is to figure out, well, where does the water flow through this building? where is the electrical current? What the hell is happening in this black box where all the individual wires go in and wires come out again? And this is the situation that you, as a software engineer, also occasionally find yourself in, because you're faced with a very large set of programs that are not always as documented as should be, or the documentation is not always up to date. Yeah, and then you have to do lots of archaeological skills or investigation skills to figure out what's actually going on.
2 important questions that came to my mind. And the first one, as we are at the definition stage, you said programming. You didn't say coding. And I have to ask you, what happened with this word? It used to be programming. Why everyone now talks about coding?
I guess it's shorter, but you can say that not all the artifacts that go into software are programs. There's also something like, say, configuration files and other parts, documentation too, which technically speaking are not programs, but they are formal. So they are code in some way. So you could also say coding instead of programming. From a bird's perspective, there's not much difference.
Okay, good. And the second thing you mentioned is something that always fascinates me is that, okay, we have, let's say, a person or even a team that writes some code, some program, and then they leave the company. And then someone else comes and is actually responsible for maintaining it. And somehow the people who created it before don't leave the exact documentation, or they are not great programmers and the code is not that great, right? So is there anything that actually helps us follow other people's way of writing, or it's a trial and error thing? Of course, we have the language, I know, but yeah.
In the last years, I've been writing 2 books on testing and debugging, respectively. And these books are somewhat special because they essentially combine lots and lots of text, as any textbook would do, with code that actually implements the techniques that I'm introducing beforehand. And this is a style that Donald Knuth, one of the grandfathers of modern computer science, has termed literate programming. That is, when you're programming something, you go and you don't just put all the program code into your editor, but you go and actually explain what the code is doing to some imaginary listener or reader at this point. This is, of course, what you exactly do when you're writing a textbook. But I found that this combination of constantly first programming a bit and then also explaining what the code is doing, illustrating this with a couple of examples, again coming up with a piece of coding, again illustrating this. This is something which, from my personal perspective, I found immensely helpful, and it has totally changed the way that we in our group here or over here develop our programs these days. So it used to be the case that our PhD students would build huge infrastructures, and these infrastructures at some point would then, essentially become a big pile of fuming code pieces, which nobody really understood except for the one PhD student. And the PhD student sometimes would leave without even leaving something like a README text that would explain, these are the files and this is what they're about and this is how to run the software. Sometimes not even that is documented. Since we changed to that style of doing this in this textbook style, explaining how things work and why they work, this has changed things tremendously because all of a sudden all of our software comes with documentation by default. And the nice thing is that even when I look at my own code months later, all of a sudden I'm happy about my past self. Hey, my past self explained this to me. Thank you, past self. And my past self is happy too. Hey, future self, this is how this whole thing is going to work. Then I'm saving time for myself eventually. This very much convinced me of the value of well-done documentation, but actually documentation that is well integrated with the code and does not come as some Word file in some separate folder that is sometimes updated and sometimes not, and typically totally out of date.
Yeah, and I also visited your textbooks, I have to say, and I really enjoyed, of course, I didn't go through all of them, but I really enjoyed the way it's written because it's brilliant way of combining exactly this theory with the hands-on practice that, we always talk about, except for just reading how you should apply the language and then going to the computer and using the compiler and everything else, right? So that's good. And for sure, we'll share the links to those textbooks in the show notes in case someone wants to start them, then maybe come and study with you. Of course, why not? But now, as you said, that those 2 parts of the software engineering, I guess we are looking at the second one, right? Because you mentioned the testing and all that in case of your research. So I thought that we already understand the programming languages. We know what we want. We write the program and then testing. We test a little bit. It works. That's it.
Yeah, that's always a good question. So yes, I definitely position myself in the second stage of software engineering. So I'm not so much concerned about how to write software, or I'm also not very much concerned with programming or programming languages. There are plenty of colleagues who are way better at that than I am. But indeed, I am typically faced with existing programs and existing software. And my job is to develop techniques that make this software reliable and that find bugs in the software, that is, find possible ways that the software does not behave as it should. So, of course, depending on the kind of software that you write, the demands on testing are very different. If you have some small program that you write for yourself, such that you can press a button and then whatever, your microphone and your recording device switches on automatically, well, that's something that you test by doing, and if it doesn't work, well, that's not very critical either, because you may still be able to start these things manually. But if you would step into, say, a commercial airplane, and somebody would tell you, well, we have flown this commercial airplane once and it worked, and so right now we are now starting putting it into daily practice, that's obviously not something that people would do. And another question would, of course, be, we have never flown this airplane, but we have proved it to be correct, so please everybody step in. I'm not sure whether this would be 100% convincing either. I guess if they gave out parachutes to everyone, maybe that would help. But you see, we want to establish some reliability and some trust into our software. And the typical way of doing this is, as I mentioned, either proving that the software works reliably, which is something that you can do at a certain abstraction level, notably when the programs are small or when the abstraction is not too complex. But for by far most software, the standard method is testing. That is, you test the software under all possible circumstances and possibly as many combinations of these circumstances as possible and check whether it does the right thing. And depending on your area, obviously, when you have safety-critical software, then the demands for testing and verification are much higher. But this is how software is being tested all day long.
But then it means that the human being has to know, okay, this could be a potential error.
Yes, one of the challenges in here that you, as a tester, normally, you have to define all these possible situations and then, well, simulate each and every one of them, which is quite an amount of coding again. For every line of code that is being written, you need something like 3 to 5 lines of test code just to make sure that this line that you just wrote did the right thing. So testing is actually way more work than actually the coding part, or at least, well, that's what it should be, unless you want your users later on to test the software. This is why the idea is to generate such tests and such inputs automatically, such that you have some sort of robot or robot programmer who constantly feeds in new inputs into the software at hand and tries to examine it with as many different test inputs as possible in order to cover all its behavior.
And this is where the S3 project comes in, I would say.
This is specifically where my most recent project comes in, because we wanted to make use of very elaborated, automated testing tools, automated debugging tools, automated monitoring tools. We call these tools robots because it's more fun to imagine them as a semi-human being, but they're also closely related to what humans are doing when they test, when they debug software, when they monitor whether the software is doing the right thing. And yes, these robots are able to generate plenty of inputs to software, to check whether the outputs of the software are correct with respect to these inputs. And they're also able to automatically find out when and why the software is failing.
And why would they be better than a human being doing it?
Because they don't sleep and because they're cheaper.
Cost, as usual, right?
Well, it's very simple. You know, computers were made to relieve humans from boring, repetitive techniques. And testing can be a very boring, repetitive technique. But we have to imagine that. Here I am at some German bank. I'm not mentioning any names. And this German bank is just about to release a new version of their banking app. Okay, banking apps are critical, so somebody has to test it. And what people are doing in industry is, let's assume this bank employs high-paid bankers that go and click through the individual functionalities of the app, and then they have a big check sheet where they put check marks. Yes, I was able to transfer €1 from my account to another account. Yes, I was able to receive €1 from another account to my account. Yes, I wanted to send $1 trillion to some bank in North Korea, and the app declined this. Yes. And the contrast of the application was okay. And the font size was okay. And all these things. Okay, there you go. Wonderful. This takes a couple of weeks to months until you have all the checks done. And then you can make a new release of your app. This is manual testing. And let's assume, hypothetically, that the German bank is actually bankers doing this thing. Then you're having super highly paid employees who may be even paid better than your IT specialist. And what they do is dump repetitive work of doing check marks. Yeah, good. That's what you can do. And now we have, say, some fintech, some modern banking thing, and their app is tested automatically, and they have a robot that does all the checking by itself and does the check marks, and it produces all these check marks within minutes. And within minutes, you already know, oh, my bank app is doing okay, which means that you can release a new version of your banking app every other day or so. And with new features, more features. And here we have this new bank, here we have this new fintech running in circles around the old legacy bank. Yeah, so it's cheaper, people don't sleep, and on top, as a company, you can be more agile, you can adapt to the market more quicker. All of this is made possible through automated testing.
You made an interesting Freudian mistake. You said people don't sleep. Well, I hope people don't, but the robots in this case.
I'm sorry. The robots don't sleep. Of course, people sleep, and I want people to sleep.
Exactly. That's pretty healthy, people, right?
And the nice thing, of course, is people can sleep better if they know that the robots are doing all the work. So, I can relax.
Well, that's a very interesting comment that people can sleep better. I don't know whether everybody would agree with that, but fair enough. How much autonomy do you want to introduce there? Is it in case of these bots that would be, analyzing and testing, we just run them, okay, they say stamped, approve, everything is fine, now it's released? Or do we have this kind of a co-testing somewhere, human in the loop situation?
Ideally, the robots would eventually put the stamp of approval in the end. Then the question is, would you step into a plane that has been entirely tested by robots? Or you could also ask the question, who watches the watchman at this point? So how well are the robots being done? Which then is an interesting question. But then you no longer depend on the robot's work, but you depend on the person programming the robots. And this is, of course, something, maybe you need another robot to check the robots, and then it's robots all the way up. That could be fun, but obviously somebody at the end of this chain has to take responsibility, and this cannot be the robots. So in the end, some human will still have to sign off, yes, either I did the testing, or I programmed the robots who did the testing, or I programmed the robots who checked the robots that did the testing, and so on and so on. But of course, the robots can only do what they have been programmed to do. This means that in some cases, well, maybe when designing what the robot has to test, then I have to step in and say, oh, the robot, please do this, please do that, please do that. And there's actually an interesting part of my research where we try to enable developers to give them means to tell the robots what to do, and not just let the robots run blindly and just happily test everything that might be possible, but to allow the developers to give the robot some guidance. In this plane, these particular parts are important, or this has been recently changed, and this is where then the automated testers should pay particular attention to.
Okay, this sounds so simple that I'm wondering why it's not done yet. Where's the obstacle?
Yeah. There's two major obstacles in there. And the first obstacle is the problem of generating inputs by themselves. That is complicated. Say, if you want to test something like a Microsoft Word with millions of Word files, well, there's two ways. You can scan the internet for millions of Word files. Sure. And since these have been produced by Word in the past, well, it's very likely that Word will also be able to process them in the future. Problem is, you're not going to get to all the difficult corner cases. Alphabets that are not the Western alphabet. Text that gets written from right to left. Deeply nested tables, all that stuff. Things that people don't use too often. Okay? And this problem, unfortunately, also persists when you're using some machine learning techniques, some large language model. If you have a large language model that is trained on millions of word files to produce more word files, that's nice, but you're going to get more of the same. And what you want to have is something that is uncommon. And so you need means for programmers to generate such Word files that actually employ the uncommon stuff. It's not a big surprise. If you use things that are very uncommon, you're going to trigger bugs. You're going to trigger way more bugs than you would trigger with what's in the ordinary part. And it's exactly those bugs that are interesting. So that's the first problem. We call this the test generation problem. And we address this problem by allowing programmers to specify the language of these files. That is, we allow them to enumerate all the individual features that can go into a Word file, and then our robots happily combine all of that, and they compose the weirdest Word files you can imagine. Things that humans would never write, of course, but that's exactly the point. The second problem is the so-called oracle problem. How do we know whether the program is doing the right thing? And this is a problem which can be very easy. I can simply say, my program must not crash. That's fairly easy to detect, even automatically. Well, if Microsoft Word crashes, there I am. I get some internal error, whatever, some dialogue. Microsoft Word has discovered a fatal error and needs to be restarted. We apologize for the inconvenience and for your last 20 pages of your PhD thesis now disappearing, but please press this button. Sorry, Microsoft does a pretty good job in saving as much as they can of the input. So
yes, you have to be careful here, I think.
I don't do justice to the engineers. No, Microsoft does all they can in order to handle errors well. So that's
some generic word processor, let's say.
Yeah, let's say some generic word processor. But the question is, does Microsoft Word then later on produce the correct output? Are the commands that are sent to the printer, and is the final result that comes out of the printer, is that exactly what the user has typed in the first place? That's something that can still be maybe easily determined. Well, the letters that you typed in also must all appear in the output. Some of them will not appear because they may appear in footnotes and whatnot. Do they come in the correct order? Do they come in the correct font? If you have some embedded table, does it show the correct results? And then things get more and more complicated the more and more functionality you test. If you want to test whether a plane does the right thing, well, when does a plane do the right thing? Well, it shouldn't crash. That's good. Yeah, that's not too bad. So it has to stay in the air. That's okay. But all the other stuff, what is correct navigation for a plane? And make it more complicated. What is correct navigation for a car? How does a car know? How can it recognize what the traffic lights are, what the rules of the road are? Is this a pedestrian? Is this a car? Is this another car? Is this a dog? All these questions. When and how can you tell whether some software is doing the right thing? And testing it, testing your autonomous car on the road is one thing, but checking whether it always does the right thing and specifying what the right thing should be, that's the big question. How can we ever possibly do that? And these two questions, so altogether these two challenges, the generation problem, how can we generate as many complicated inputs or as many situations as possible? And the second problem, how do we check whether the program is doing the right thing? Yeah, these are the big challenges in testing and by extension in all software development, because it's a fun quote. If you have no specification of what the program should be doing, you have no errors. You only have surprises. And, well, as I said, a surprise in your own written script that sets up things, that's not too bad. But, when you're in a plane, when you're in a car, surprises is not an option.
Totally not, right? And then it's also the question of the success rate, right? How do you know that the test is successful or not?
Yeah, so that's exactly the thing. In order to check whether a test is successful, you have to tell it somehow what the expected behavior should be. And if you want to make this in all generality, what is the correct behavior of a word processor? What is the correct behavior of an autonomous car? Yep. That's complicated. And there may even be situations in which there cannot be a correct behavior because you may be in a lose-lose situation, as with autonomous cars, that both the alternatives of what the car could be doing are both disastrous and we don't know what to do. But that's typically not something for engineers to solve, but for philosophers to talk about.
Exactly. That's what keeps them up at night, coming back to the sleep discussion.
Super complex. That's what keeps them at night. For the engineer, the question is always, have I tested enough and have I tested it well? And can I release this whole thing? For the philosophers, the question is, what should the software actually do at the end? And this is not always easy to solve.
As you're looking at it from an engineer perspective, one more thing to quantify. How much is enough for testing? When do we say, okay, we've tested now?
In hindsight, there's never been enough, because in hindsight, when software fails, this always means that you haven't tested enough. That's it. When software works all day long, nobody asks that question. So as a tester, in a way, you're always in this unfortunate situation. You're never praised for your software running well, but you're always blamed when software does not run well. Having said that, I'm always amazed at how blindly all of us these days rely on daily software, and how blindly we can rely on our software. And this is to quite some part because of modern software engineering and modern software testing doing the right thing and doing it well.
Yeah, absolutely. When a couple of months ago there was the blue screen of death at airports, right? We kind of got reminded. I mean, I went back to my past times when it was so normal, the blue color that just reminds you of, something's crashed.
Yeah, that's correct, and that of course was something that was not well tested, or was not tested enough. Having said that, on 364 days a week, all of us who go to the airport apparently are able to check in just normally and get to our seats, and the plane just fly. It's always fun and, of course, sometimes very damaging to see software not working, because, as I said, we so much depend on it, and there can also be very, very sad stories associated with software not working. Think of medical software, think of safety critical software. But being the optimist who I am, in most cases, things just work. And if you imagine the technology it takes to fly from A to B, the technology it takes to be in India and put your card into an ATM and get money out of it, these are marvels of modern technology. When you think about all the possible things that could have gone wrong and that don't go wrong, I'm always impressed by that.
Yeah, me too. I'm also impressed with my kids' impatience when it comes to how software runs, because they're just especially with games, I remember just putting a game on and then just having, I don't know, some water and toilet break and whatever. And they just if it doesn't run in 2 seconds, they start complaining already.
Yeah, we start making impossible demands on our software these days. Yeah. But yes, come on, it's fine.
Yeah, that's something we discussed with Jordi as well. So yes, exactly. That's a problem. Maybe the expectations are too high. But yeah, there are two things that you also look at, and I just was wondering, for those of listeners who are more into definitions and want to understand what the researchers in software engineering do, the first thing I wanted to know is also fuzzing, because we talked about testing, but there is fuzzing as well. And what is that, except for the word that I know, but I think in the context is something else.
Fuzzing is a particular way of generating plenty of inputs for software. And you can imagine fuzzing as a monkey hacking on a keyboard and generating just random inputs and see what the software is doing with it. The monkey could also do vague mouse movements, but a monkey hacking on a keyboard is more fun. Now imagine that monkey hacking at an incredible speed that is producing thousands and thousands of keystrokes per second. And on top of that, imagine not just one monkey, imagine 1 million of monkeys all day long hacking everything together. Okay, good. It has been said that if you just put in enough monkeys and give them enough time, they're going to produce all the works of Shakespeare, including those that Shakespeare wanted to write but never got to it. Unfortunately, that doesn't work because you need an insane amount of monkeys to do that. The nice thing, however, is that with all these random inputs still, all these random keystrokes, you tend to cover plenty of features in software that is indeed operated by such keystrokes. And what you can do with these inputs is you can test software pretty well for robustness. That is, how well can it cope with unexpected inputs? And since most programmers, being the high-paid folks under pressure who they are, tend to first focus on the regular inputs, that is, they tend to focus on test what the software actually is doing. They sometimes omit testing for entirely unexpected inputs, and software can very easily stumble over unusual, say, names. If your name does not have whatever 6 to 20 Western characters, but all of a sudden comes along as a string of whatever 2,000 characters, which combines not only letters, but also digits and punctuation marks and whatnot. There is software that sees that and then all of a sudden stops working. And this is particularly interesting because lots of security flaws can take place in software that doesn't handle such long or weird inputs correctly. So when software processes your name, for instance, all the individual characters are stored in an area of memory, which has often a fixed length. And if you give it some super long name, then the characters that you put in spill over that length and they exceed into the next piece of memory where something entirely different normally would be stored. And this can lead to the software behaving entirely differently from what it was originally designed for. In many cases, the software will just crash. And if it crashes, then this is interesting from a security standpoint because this gives you a means as an attacker to crash the software. And then you can, for instance, crash whatever, some train software, or you could go and crash some tax software, some administration software, whatsoever. Or it may also give you means through some sophisticated attack by coming up with more sophisticated sequences of characters to actually get information out of the software that was not intended for you, for your eyes. And there are a number of such attacks that all have been discovered by fuzzing, that is, by simply sending zillions of random strings to the software and hoping for the software to not recognize these and not handle these in the way they should be handled, namely simply be rejected. This is an important testing technique, and it is very much recommended before you release any kind of software or service to the world to also subject it to common fuzzing techniques such that such attacks can be thwarted from the very beginning.
So I get from what you said that it is recommended. So that does not mean that everybody does it. That's a second layer of testing, let's say.
Well, the thing is that if you as a developer don't do it, then someone else will do it at some point.
Okay.
And if someone else finds a bug in your software, then the question is, what are people going to do with that bug? So if I find a bug in some important piece of software, then, well, I'm being paid for finding these, so I report these to the original manufacturer, and the original manufacturer fixes things. So far, so good. A couple of years ago, some of our students found an important bug in our student administration software. So the software company installed that software, and 3 hours later, with fuzzing, some of our students found bugs in there and said, hey, actually, I can change my grade to any grade I want. What do you think of that? The reaction of that software company was they wanted to sue the students for finding bugs in their software, which is not exactly what you want to have.
No.
No, not at all. And so, of course, our university president, everyone said, no, come on. You sell us software that is obviously vulnerable, so please fix that. What you want to have there is you want to fuzz, that is, thoroughly test your software yourself, obviously, and not only with common inputs, but even more so with uncommon inputs. And this is also what I research, coming up with uncommon inputs that go beyond just random strings of text, but coming up with something that looks a bit more like regular inputs, but still has a couple of twerks sometimes hidden in there. And the second thing that you want to have is, after you have tested yourself, well, you actually want others to test your software. So what many companies do these days, they set up bug bounty programs and they say, okay, if you find a bug in our software, tell it to us, then we give you a few $1,000s, for instance. Thank you very much. This, of course, also comes with a piece of fame. So then you can later claim that you found this important bug in the software. Well, the alternative is for you, if you found such a bug, well, you can also sell it to some attackers, to secret services or whatnot. Then you may be able to make more money out of it. But, well, it's a shady business. Maybe the buyers also want to silence you afterwards. Not sure whether it's worth doing that. But, there's also a market for such exploits, that is, carefully designed inputs that trigger bugs in other people's software.
But once your project is over, there will be no need, because you can just use one of the bots that you will develop, and then they will do all the job, and all the bounties and everything else will go to the research group.
Unfortunately for us, we don't collect bounties, so these don't go to us. We live by the fame, and anyway, it's our professional job to find such bugs, so that's what we do. But there is indeed a risk here in the research that we're doing, because the tools that we build can always be used for finding bugs, and our techniques are neutral in the sense that we don't care whether it is the maker of the software themselves who employs these tools, or whether it's the attacker who employs these tools. And there's a particular domain where we face that problem immensely. That is in the domain of public administration software and business software. This is software that exchanges data via a standard called XML, which is very popular in business software. And we have developed rather as a side effect of our regular research, techniques that can happily test the software with very well-formed XML data that could, in principle, uncover plenty of bugs. Well, and it turns out that this software has never been tested automatically and therefore is very vulnerable to such attacks. And yes, in our early tests, we already found dozens of vulnerabilities this way. Yeah, and this gave us a typical ethical problem. If we release these tools, who will be faster, the attacker or the defenders? And the way we are addressing this right now is we created a spin-off, a startup that deals with that problem by selling not the tools, by keeping the tools to ourselves, and by hopefully selling the test cases not to the attackers, but to the defenders. At least that's what we hope for, that the people who are buying the test cases, well, they have to come up with a legit reason. Then we can thwart that risk for quite some time. But in all generality, yes, if you're dealing with fuzzing tools and if you're dealing with testing tools, there always is this problem of proliferation, that your tools can be used either by attackers or by defenders, which is why I'm always happy to recommend, please everybody make use of our open source tools and test as much as you can.
Yeah, a very good thing. It's all about also people being interested enough and finding the time and the means to actually use it, right? And
but as I said, if you don't test your software well, someone else may at some point, and that is going to be way more expensive than if you do it.
True. We only have 2-3 minutes left of our discussion, so I just wanted to go back to the last thing I was wondering when I was reading some of your articles and other publications online. And it's something that goes back to one of my passions, but in this case, space mining. So we're talking about mining, but mining in the context of software engineering. I was wondering what that is, because that was the grant you got before from ERC for mining. And I just wanted to understand because I don't know.
Mining is a term that comes from data mining, which again comes from mining rocks and mining physical activities. You dig deep into a piece of software in order to find out findings for that piece of software, important data and important features of the software. And what we have done in the past was mining from program executions, that is, figuring out how programs normally operate in order to find anomalies. What we also have done is data mining on version histories, on how the software was developed, by whom and when and why. And what people, of course, are doing these days too is data mining lots of program code. That is, this is what normal code looks like, this is what unnormal code looks like. And it's all this data that is being mined, mostly from code these days, but increasingly also from the development of the code, and in the future also from executions of code, that drives these wonderful large language models that tell us this is what your code actually should look like, or this is what your code could look like. That is, the mining techniques provide the data that these learners, that these language models learn from, and are thus then able to tell us more about how to code and where our software behaves correctly or not. So data mining is the first step, and then all the processing comes into these AI things, which I think will be subject to another podcast at some point.
Exactly. That's what I was thinking. This is opening another, I don't want to say Pandora box because that's a bit negative, but you used the word wonderful in front of LLM. So let's stay positive here. But yes, very, very interesting. And listeners, if you were waiting for the pop quiz today, unfortunately, we did not have time to ask that question, but I'm sure you learned a lot from the discussion. And what remains is to thank you, Andreas, so much for today and for sharing a small part of your world.
Thank you very much, Hannah. It's been a pleasure.
This is it for today. Don't forget to subscribe, to follow us, to check what we are writing, suggest guests, and remember we are present on Patreon. So if you like what we're doing, support us as well. And this was Silex, and my name is Hanna Siemaszko.